Hey there. Okay, so we're going to get started with Module 3 today, going over kind of like the fundamentals of seismic attributes, and throughout this module we'll be doing a review of a lot of the different attribute types and what they can be used for. So, let me progress. A lot of these lectures come from many resources, and I'm going to go through this information really quickly. So I wanted to mention that we have a lot of information up on my ASPE website that you could find just by Googling like University of Oklahoma ASPE. And then there's more detailed information also in some of Dr. Marfort's books that were released back in 2007 and then 2018. And so the reason we study seismic attributes is because we really want to have a way to see more in the seismic data, as I've mentioned. We want to provide kind of more objective, more quantitative measurements to enhance or supplement our traditional interpretation on the amplitude information. And so what attributes allow us to see is kind of more of the patterns so that we can identify and characterize those geologic features that might be a little bit more on the subtle side in this original seismic data. Seismic attributes can also allow us to really quickly go through an entire data set and see some of those larger scale features. And I kind of see them as a way to bridge more of the qualitative interpretation with the quantitative analysis that we do. And so what I'm going to show you here is just a vertical line. So we're going through the Cora 3D survey. So this is offshore New Zealand in the Taranaki Basin, just a little bit to the west of the North and South Islands. And when we look at the seismic data, we can see a lot of patterns in here. And we also happen to have a few wells. And so I've pointed out already some carbonates. Here's some of the wells. This is the Cora volcano itself. And so we can stare at this. This is one of my favorite images and data sets we use for lab in class. And so we can see a lot of different features from slope channels to mass transport complexes. We can see patterns related to progradation, some basin floor fans, and then also some slope channels right here. And so a more skilled interpreter, we can look at this and we can identify those maybe a little bit quicker if we've looked at seismic for a little bit longer, or if we're very familiar with the area and know what geologic features we might expect. So we call that in-context interpretation. We can also look at it more, and we've got kind of this section right here I've pointed out as marine shale. There's not a lot of patterns in it. It's very kind of transparent is what we would call it, because we don't have those reflection coefficient differences or acoustic impedance differences to cause reflection coefficients. And so you don't see the interfaces quite as well. Over here, we have an interesting pattern, which are some tuffs and clastic features. And then there's a whole bunch more that are related to the volcano itself. Well, most of them are. We've got volcanic mass transport complexes. We've got some evidence perhaps of lava flows, and we know that because we've tied it to the well in the area. Here's the magma conduit up in this area. We've got pyroclastic flows, again, something we've tied to the well. So we've incorporated the well to enhance our seismic data. And then a bunch of sills that we've pointed out as these bright reflectors. And so what we often will do when we start using seismic attributes, or trying to dig down into particular features, so digging into the seismic data more for more detailed interpretation, is we'll think about, and I've alluded to this in some of my earlier lectures and shown you some examples, but we'll try to understand, okay, what does it look like in seismic? What does it look like? What attributes might help us? And so I'll go through a couple of cases in this lecture, just showing you what you can do when you do your own interpretation. And so here we've got some incised channels. You can see it in a time slice right here. We've got the channel. We can also see some channels of various sizes in this vertical slice. And so what is ideal to do is to think about, again, break down the problem from the geologic facies. So here we've got an incised valley. We want to think about what's the visual expression of these features in seismic data, from the internal reflection configuration with the subparallel reflectors to the external form. We've got different attributes, kind of main attribute groups that we'll want to think about, from the amplitude, so how variable is it? That'll give, it'll vary depending on the fill of the channel or valley system. In terms of coherence, will coherence give us information? In this case, yes. We'll get kind of that external low coherence edges of the channel. Dip and convergence, so we can break down what we would expect for channels. They would be parallel to subparallel. They perhaps become convergent at the edges of incisement if the channel bases happen to be imaged, which they aren't always. Curvature, we could see some anomalies related to compaction. The spectra, we can get very variable spectra information depending on the fill thickness. So spectra, we're working more in the frequency domain. And then texture, again, is something that's dependent on fill. So this is a very typical way we should be breaking down and thinking about our seismic attributes. Here's another case where we've got some progradations. We can look at them in terms of their seismic amplitude and then think about what they would give us in terms of the seismic attribute response. So these, we would have cliniforms. They often have that sigmoidal shape, so that would be their external form, and we would see them bound, like the sigmoids would be bound with the top and bottom sets. Amplitudes are often moderate to high. Coherence can often be moderate to high also, and then low at kind of the terminations. So let's see, we've got some terminations kind of over here, a little bit more over here. Dip and convergence, we would see in those attributes that they would be kind of subparallel and then converging. Curvature, we'd get some information. From curvature too, it would be positive and negative curvatures that we would pick out. In this case, we've got some channel cuts into these progradations. And then our spectra is typically pretty high with progradations, and the texture would be very low entropy if we were doing GLCM. Here's a case of the volcanic mass transport complex. Again, we know it's volcanic because of the well tie in the area. So the well is right around this area. I don't have it kind of projected on here. And again, there's no great reflections inside. The external form would look very chaotic. Sometimes you can see kind of coarse inclusions. Looks like we got one right around here. I'm trying to circle. The amplitude tends to be very variable from lows to highs, again, depending on the lithology of the particular mass transport complex, which in this case has volcanics, so that would cause that higher variation. Coherence is incoherent because they're very different from each other in these mass transport complexes. The coherence is always very high and incoherent. We've got dip, curvature, spectra, and then the texture would have a very high entropy too. And then just to go through a few more, here we've got charged sands, so methane or CO2 charged sands. We've got this bright spot, and so here's the core volcano, and then we're looking above it quite a bit. We've got this bright spot right below the seafloor, which is just cut off. So internally, it looks like a bright spot, so it's got that high amplitude. The external forms would be a higher amplitude anomaly. It could have a different phase of the seismic. It would be coherent. In this case, you have a flat dip because it's related to gas. Curvature, we tend to not see these fluid effects in curvature. Spectra, it would be broadband to a low frequency response. Oftentimes the higher frequencies are attenuated a bit, so it might be on the lower frequency side, and a very low entropy. Here we're looking at some channelized turbidites, so we can look at them right in this area in terms of a vertical slice, and here we've got a lovely time slice, both of these from Kurt Murford's textbook. And in this case, we could, again, I'm not going to go through, I have like 20 examples, so I'm not going to go through any more after this, but we can think about the internal reflection configuration, which in this case would be parallel to subparallel, moderate to high amplitudes. They may lie on an unconformity on deeper strata. They tend to be moderate to high amplitude, moderate to high coherence. And we'll kind of break down through this. All like this full chart is in Dr. Murford's textbook if you want to look at it. Or you could shoot me an email and I'll send it to you. So anyway, so that's hopefully gives you an idea of how we'll start thinking through the attributes and how it's using tables like this and kind of breaking down what the geologic response would be in seismic, and then how it would appear in different attributes is a good way to communicate your information that you're seeing as a seismic interpreter to the rest of your team. And so I like this example that Kurt put together of trying to think about, okay, so what are we doing as the human? Like what's going on in our head? And so he has this landslide example. This is a landslide in Washington State in 2009. And if we're looking at it as geologists, we kind of pick up some contextual clues about what's going on before we even call it a landslide. And so that could be like the unconformable contact with the highway beneath it. Okay, so you pick out that contact right in here. You might also see the scarp and then, think to yourself, oh, that's a landslide. So that's kind of trying to break down the thought process that we have. And so when we think about it and then relate this to seismic data, what we first see is, okay, well, we see this low coherence. If we were to look at this in an attribute, it's broken. So there's a low coherence between it. We also have a bit of heterogeneity from this landslide. And so that would show up perhaps in like GLCM entropy as a seismic attribute. And then as the landslide happened, the layers are no longer parallel, they're non-parallel. We may see some reflector convergence at the end of that landslide, at the terminus of it. And so all of these we can kind of put together is what we're doing if we break down what we did in like 3 seconds looking at this image to call it a landslide. And so what we would expect with all of these observations is a mass transport deposit. This is also when we start talking about machine learning in a few more lectures. This is what's happening in clustering is like machine learning is able to unsupervised clustering methods are able to take these observations and then where they overlap, be like, okay, well, we're seeing, this feature in coherence, a low coherence, a higher GLCM entropy, a non-parallel layer, and all of that to us creates a cluster, which then we as the human would go in and call it a mass transport deposit. Okay, so one of the things we always want to be aware of is not to put too much interpretational bias into what we're doing. And so we just want to be aware of, are we considering all the possibilities of what this feature could be? And so just an example of like a confirmation bias that we've put together. So here we've got a seismic image. We want to understand, okay, what are we looking at? We see some mounds here, and perhaps we go in with a pinnacle reef in our mind. Okay, so we've always worked carbonates. There's research that suggests what we've thought about a lot is what we're going to see in the seismic data. So I've spent a lot of time working in the Gulf of Mexico, so I always see salt first, and then I have to remind myself, not everything's salt, Heather. So what are the other possibilities? So it's always good to try to remind yourself that you're going to have bias before you go in. Anyway, so if we go in thinking, okay, these are carbonates, we can easily see carbonates, pinnacle reefs in this area. And I have kind of put some interpretations on this from, okay, here's where the pinnacle reefs are. We can see some associated faults, kind of that fault-related fold. We've got some artifacts of that pull-up from the pinnacle reefs. But then if we are aware and we are open to seeing other things in the seismic data, one of the things that often gets confused with pinnacle reefs is volcanics. And so now we could go in and think, okay, well, maybe it was pinnacle reefs. Maybe I should see if volcanics would be a viable interpretation also. And so going in here, I've picked out in red kind of a sill feature. And if we assume that that's a sill, we can pick out some of the forced folds from that sill being intruded. We could see the related deformity. We could also notice that maybe instead of pull-up that we are seeing in the Pinnacle Reef, that we have more of the magma conduit. It's very noisy and hard to pick out. Perhaps some dikes in the area, and then instead of a Pinnacle Reef, it's a volcano. And so we want to keep all of this in mind. I like to mention bias throughout my lectures, just to remind you to do the background research, like never jump into a seismic data set without any prior knowledge. Okay, so seismic attributes can be arranged in many different ways. I'm going to show you 2 different ways. So this is a way to think about seismic attributes in terms of the physical properties that they measure. And I find this way very useful because often when we're looking at seismic, we have already an idea based on our background knowledge of what features we may expect and what they may look like in seismic. So in this case, the way we could break down this is things from structural attributes. So these would be things that measure dip, curvature, aberrancy, reflector coefficients, reflector convergence. We could see discontinuity. So these would be reflector configuration attributes, spectral attributes for magnitude, phase, frequency, measurements, including those instantaneous attributes that I'll talk about next. Texture attributes, so these would be our amplitude gradients, curvature, GLCM, gray level co-occurrence matrices. We often have kind of our impedance attributes. Sometimes these are called geomechanical attributes. So this would be AVO, acoustic or elastic impedance, and then those related to geomechanical properties. Anisotropy can give us information about velocity, amplitude, frequency versus azimuth. And then time lapse, which is changes in amplitudes, travel times, and spectra. We can also divide our attributes this way, which is more based on the input data. And so sometimes if you have limited input data, you can think about, all right, now what attributes can I collect with this information? So horizon-based attributes, these would be like your time structure, your dip magnitude and azimuth, curvature, your geometric attributes. You could do shaded relief maps or bump maps. You also have your formation and window-based attributes, so the thickness, the RMS amplitude, optical stacking, counting the number of zero crossings. You can have your single trace attributes or instantaneous attributes, which would be also include your amplitude, waveform shape, spectral decomposition, acoustic impedance. You have multi-trace attributes, so where you're doing an attribute on multiple, the calculation of the attribute is on multiple traces, not just one seismic trace. And this would be coherence, like SOBO filters, curvature, amplitude gradients, GLCM textures. And then if you have pre-stack information, you can do your interval velocity, pore pressure, AVO, your azimuth related analyses, elastic impedance, lambda rho, mu rho. And so a lot of these that I've just shown in the last 2 slides, I'm going to go over very quickly in the next in the next series of mini lectures. Okay, so to wrap up this, I just wanted to mention kind of 6 common ways that we often use seismic attributes. And so the first one is to communicate to your team member or management or other partners about a given interpretation or play concept using the least amount of slides as possible. Sometimes as a seismic interpreter, we look at things, like scrolling through an area very interactively. But when we do a presentation, we've got to kind of cut that down into like the 5 slides that were allotted. And so we want to put as much visualization into a couple of slides as possible. And so here's an example of showing the kind of honeycombed hexagonal and a kind of elliptical syneresis features that may end up giving us some drilling problems. And so we could very easily see that in the seismic data. Another way is or another reason to use seismic attributes is to extrapolate very sparse well measurements of reservoir thickness or porosity or hydrocarbon saturation, as well as kind of use them as prediction tools, which may include our multivariable statistics or geostatistics and neural networks that we're going to apply to those seismic attributes. And so this is an example of showing prediction of rock type based on the properties we see in seismic, and so this may be interesting to completion engineers. Another way that we'll use seismic attributes is to kind of represent or reconstruct the tectonic or depositional and diagenetic history, which will allow us to better infer the lithology, infer the porosity, kind of understand perhaps the condition of the seal or fracture density. And so this is an example from the Alaskan North Slope, where we're using curvature and coherence to really pick out all of the fracture and fault patterns. And then over here, we've got the Red Fork channel system in central Oklahoma, where we've used some phantom slices on a multispectral coherence volume to show up this feature, which is really difficult to pick out in seismic data. The fourth one is to communicate how complex the geology could be to others. So keep in mind that attributes don't create new information, but rather they allow us to see more in the information. And so we may need to really quickly show the complexity perhaps to our engineering team. Like here we've got a bunch of joints and karst features that we can see in the most negative curvature. Over here we've got some very subtle channels that we're picking out with the coherent energy gradient. Another reason is that we'll use seismic attributes is to help evaluate the effectiveness of alternate processing methods. So for mapping and understanding our statics or our velocities, different filters we may want to apply, or migration algorithms. And so here's looking at coherence on two different migrated volumes, doing, kind of processing workflow A versus processing workflow B. And we can see that we've got, with improved velocities on B on the right-hand side, that the coherence is much more clearly showing these channels. And then finally, we can use attributes as inputs to machine learning. And so here we've got and this has been really helpful for seismic facies classifications, for identifying fault systems and patterns really quickly. And then it's really good for, we could use machine learning to statistically correlate drilling successes or failures to seismic data volumes and also geomechanical kind of properties. And so on this left-hand side, we have a facies classification that used probabilistic neural networks to quickly identify salt and mass transport deposits. And then over here on the right, we've got an example of the cost of penetration related to seismic data using proximal support vector machines. And so just to wrap up, and as we go into the next series of modules, I want you to keep in mind a lot of these overarching ideas of seismic attributes, that they can serve a lot of different purposes. So they validate our interpretations. They allow us to extrapolate the well data from the well out into the seismic. We can get a lot of information about tectonics, sedimentary patterns. There's many ways we could classify attributes, and there's hundreds of them out there, which I'm not going to talk about them all. So they can look at the spectrum, they can look at discontinuities, they can look at textures. They also can be classified by the input data. So maybe you want to calculate the attributes based on the horizons, or maybe you have pre-stack data and you could calculate different attributes with those. I should also, remind you of the interpretation bias. So as, interpreters, we go in and we see what we're most familiar with. And so we always want to pause as we're doing our interpretation and make sure that there are not other geologic explanations that we're not considering. And of course, successful attribute analysis really depends on incorporating as much data as possible from, integrating what's known about the geology, well information, if we have production information, all of that allows us to do a better seismic attribute analysis. And that as we start going into using multiple seismic attributes and machine learning, we can really leverage seismic attributes. And this is what a lot of my research is on currently. We can leverage these seismic attributes to get even more information out about the subsurface, from classifying facies to rock properties to even production data. All right, thanks. Thanks for listening to this module.